now that we have introduced several examples from biology, chemistry, and physics that can be modeled by a system of differential equations, we're going to turn our attention to solving linear systems of differential equations. In particular, we're going to look at a system of two first-order linear ordinary differential equations where there are equations for the derivative of x and the derivative of y. Each one of these equations is going to depend on both x and y, as well as possibly a function of t. In all of the examples I presented before, the coefficients of x and y were constant, but these coefficients can depend on t, and we still have a linear system of differential equations. We can express these systems in matrix, in vector form, where we're taking the derivative of the vector x and y, and that's equal to a matrix that contains the coefficients times the vector of x and y, plus another vector that contains the functions of t, g1, and g2. So our convention will be to let capital Y be the vector that represents the solution x and y, and A of t will be our matrix, and capital G of t will be the vector representing the functions of t, g1, and g2. Now, we can talk about whether the system is homogeneous or not. The system is homogeneous if capital G of t, which I've written as a row vector with a transpose here, but if G of t is equal to the 0, 0 vector, again, I'm writing it as a row vector with a transpose so that I can use less space. The system is homogeneous if G of t is equal to just 0 for all t. If G of t is not equal to the 0, 0 vector for some t, then we would call it non-homogeneous. We call the system autonomous, just like before, if A of t is equal to just a constant matrix A. So it does not depend on t. Now, a solution is not going to be just one function, but it's actually going to be a set of two functions, x and y. And we can express this as the vector capital Y. And so a solution will satisfy, it'll be the set of functions x and y that satisfies the system that is given. Now, an initial value problem is the system above, so the differential equations that I've shown above, plus a set of initial conditions, say y of t0 equals the vector x0, y0. Again, just because normally it's going to be a column vector, I'm going to put a transpose on there. And we talked a little bit about equilibrium points, and equilibrium occurs when dx dt and dy dt are both equal to 0. So if we have a solution x and y where the derivatives of those two components of the solution are both 0, then we have an equilibrium. There's an existence and uniqueness theorem for systems of differential equations. In particular, I'm going to talk about existence and uniqueness for these linear differential systems of differential equations. That says that if my coefficients in the matrix are continuous and the functions g I of t are continuous, then our initial value problem, which written in matrix form is y prime equals a of t y plus g of t, plus the initial condition y of t0 equals x0, y0, has a unique solution on that same interval where the coefficients, the a of t's and the g sub I of t's are continuous. So this existence and uniqueness theorem is just for the linear differential equations. We did something similar when we talked about linear second order differential equations. Now the question becomes, how can I solve this system of differential equations? Y prime equals a of t times y plus g of t with an initial condition. Well, just like when we were dealing with second order differential equations, I'm going to work with solving the homogeneous equation first. So first we're going to solve y prime equals a of t times y. So I'm going to look first at two solutions. I'll call them capital Y1 and capital Y2. Each one of them has components of x and y of t. And I'm going to let them both be solutions to y prime equals a of t times y. What that means is that y1 prime is going to equal a of t times y1, and y2 prime is going to equal a of t times y2. Okay, well, is the sum of two solutions a solution? Just like when we were dealing with second order differential equations, is the sum of two solutions actually a solution? Well, let's see. We're going to do y prime, which would be the sum of y1 prime plus y2 prime. But we know that y1 prime is a of t y1, and y2 prime is a of t y2, and we can factor out the a of t, leaving us just with y1 of t plus y2 of t. And so y prime does indeed equal a of t times y if y is the sum of two solutions. Now, is a constant multiple also a solution? Well, y prime in this case is going to be cy1 prime. That's cy1 prime. I can take the constant out of the derivative. And that's going to be c a of t times y, which is a of t times cy1. And so that is just a of t times y. So again, y prime equals a of t times y. So yes, a constant multiple of a solution is also a solution. Well, that tells me that, again, just like with second order differential equations, the solutions to a homogeneous system of two first order linear differential equations, y prime equals a of t times y, form a vector space. Now that vector space is a vector space of dimension 2 because I have two equations that I'm working with. So the basic idea to solving the homogeneous equation is going to be to find two linearly independent solutions that form a basis. So this is just like the second order differential equations that we did earlier, where we had to find two linearly independent solutions that formed a basis for that vector space. So how are we going to show that once we have two solutions that they are linearly independent? Well, it's going to be very similar to what we did with second order differential equations. We want to show that c times the vector y1, c1 y1 plus c2 times the vector y2 equals 0 implies that both c1 and c2 are equal to 0. So we want to show that a linear combination of our solutions being 0 means that the coefficient C1 and C2 is equal to 0. That's the definition of linear independence. Okay, so let's take that further. So we're going to let C1 times, we'll call this x1, y1, plus C2 times x2, y2 equals 0, 0. Okay, or we can write that in matrix vector notation as x1, x2, y1, y2 times C1, C2 equals 0, 0. Okay, so we have now a system of two equations and two unknowns. When we were dealing with second order differential equations, we had to take a derivative in order to find that second equation. But here we naturally just have two equations and two unknowns. Okay, the only solution is that C1 equals C2 equals 0 if and only if our matrix is invertible. Of course, how do you show that a matrix is invertible? You show that the determinant of that matrix, x1, x2, y1, y2, is not equal to 0. So when we take the determinant of that matrix, we call that the Wronskian. Okay, so this is a different definition of the Wronskian than last time. So we're going to define the Wronskian of two solutions, y1 and y2, as equal to the determinant of the matrix whose columns are formed by y1 and y2. And so if that Wronskian is not 0, then we have linear independence. So our theorem says let the Wronskian of y1 and y2 be the determinant of the matrix formed by y1 and y2. If the Wronskian is not 0 for some t in some interval a to b, then y1 and y2 are linearly independent on AB. Okay, so if we can find two solutions and those two solutions are linearly independent, then we have enough solutions to form a basis, and they therefore necessarily span our whole vector space. So our goal will always be to find, for a 2x2 system like this, a system of two equations that have two unknowns in them, we're going to try to find two linearly independent solutions. Now, once we've solved this homogeneous problem, okay, we will know that the solution, which maybe I have not mentioned here, this general solution will be y equal to C1y1 plus C2y2. Okay, once we've solved the homogeneous equation, now we want to move on to solving the non-homogeneous equation. So again, like our second order linear differential equations examples, once we solve the homogeneous problem, that will be part of the solution, and then we'll also want to find at least one particular solution to the non-homogeneous problem. So we'll start with y1 and y2 being linearly independent solutions to our homogeneous problem. And then we'll have a particular solution that solves the non-homogeneous problem. Okay, then I will make a guess that my solution, just like before, is going to be a linear combination of the homogeneous solutions, the basis for the homogeneous solutions, and then plus a particular solution. So the derivative of that is going to be C1y1 prime plus C2y2 prime plus yp prime. Now, C1 times y1 prime is going to be A of t times y1, and y2 prime is going to be A of t times y2, and yp prime is going to be A of t times yp plus g of t. Again, like before, I'm going to factor out an A of t, and then what's left is going to be C1 y1 plus C2 y2 plus yp, and then plus g of t left over. But of course, what's in parentheses is actually just y of t, so y prime of t is equal to A of t y of t plus g of t. So just like before, our solution is going to be formed by looking at a linear combination of the basis vectors that form the solution to the homogeneous problem, okay, and then a particular solution. So here we have kind of a theorem that we've just proven, that every solution to the non-homogeneous system of first-order linear differential equations, y prime equals A of ty plus g of t, has the form, what I like to think of as the homogeneous solution plus a particular solution, okay? In this case, that is C1 y1 plus C2 y2 plus a particular solution.